This is part 8 of the integration topic, and we're going to be looking at integrations involving trigonometric functions. We're first going to start off with looking at derivatives though, just a quick refresher. So what's the derivative of y equals sine of x? Well, let's use Desmos to help us see what's happening visually. So we have sine of x here, the red curve, and we've got a movable point, and we can see the gradient changing as we move along y equals sine of x. The question is, what's the value of the gradient at any given point? So let's enable this point now, which is plotting the gradient value. So I've got a gradient of 1. As we move along, we go through a gradient of 0 at the top, then we have negative gradient, getting to another 0 gradient again, and back to 1. And obviously the cyclical nature of these trigonometric graphs meaning that that will just continue. So what curve is this orange point tracing out? It's the cos curve. So the derivative of sine of x is cos of x. And if you want to play around with this with a few of the other trigonometric functions, I'd encourage you to do so. If we focus on y equals cos of x, and we look at what's happening with the derivative, we find that the derivative is not sine of x, but rather minus sine of x. And also our third identity, y equals tan of x. The derivative for this is a little more complex. It happens to be sec squared of x. So remember that sec is 1 on cos. Okay, 1 on cos of x. And so therefore sec squared is 1 on cos squared of x. So now that we've refreshed these derivatives, we just need to sort of do the opposite process, remember, for integration. So when we integrate cos of x dx, we just go back to sine x plus our constant of integration. When we integrate sine of x, however, we just need to be careful of the negative. So the integral of sine of x is negative cos of x. And the last one, the integral of sec squared x dx is tan x plus c. Now we can't forget the chain rule, of course, so we can apply very similar chain rule to what we've seen previously to trigonometric functions. So we know that the integral of cos is sine, but let's just take another moment to remember what happens when we derive. So let's say we had y equals sine of 2x. Do you remember what happens with the derivative? In this case, the derivative of the inner function, 2, comes out the front, and then we apply the derivative to the whole thing. So the derivative of sine is cos, and so we'll get cos 2x. So, applying this kind of thinking, just like we've done before, the derivative of what's inside, a, needs to be accounted for. So we still get that the integral of cos is sine of this same inner function, but we need to account for the derivative of the inner function, which is a. So we have a 1 on a out the front. There's our constant at the end, but that's it, right? That's the basis of the chain rule. So we just apply the same thinking to the other two, keeping in mind that we need a negative for when we integrate sine, but we still have that 1 on a out the front. And sec squared, when we integrate, we still get tan, but we need the 1 on a out the front. Okay, so with our basic rules and our chain rules done, let's do some examples. Example 1. The integral of sec squared x dx between 0 and pi on 3. So we've just seen that the integral of sec squared is tan. So that's nice and easy. And then we have our limits, or our lower and upper bounds. Tan of pi on 3 is the first one. And then tan of 0 is the second one. Tan of 0 is just 0, so this bit's going to go, and tan of pi on 3 works out to be the square root of 3. Done. Second example. Sine 3x is what we've got to find the integral of now. So this is where we've got to use the chain rule. So we know that the integral of sine is cos, right? Or it's minus cos, so we've got a minus out the front. We're going to have our cos 3x, but then we need to account for this 3. So we're going to put 1 over 3. And then we have our cos 3x. And our constant of integration on the end, because this is indefinite. So just focus on here. If you had to derive this, the derivative of cos is minus sine. So the minuses would cancel out, which is good. We have no negatives here. The 3 would come out the front and cancel with the third, which is good because there's no extra constants out the front here, and we would just be left with sine 3x. That's it for example 2. Example 3. Find the integral of cos x. Well, it's not just cos x though, is it? What have we got up here? This is a degree symbol. So this is telling us that x is actually in degrees. And so far, we like to work in radians. Right? Radians makes things nice and simple for us when we're dealing with trigonometric functions. So we can't just go and say that this integral of cos x is sine x degrees, because it doesn't match up. So we actually need to convert x degrees into radians. The key to remember here is that pi radians is equal to 180 degrees. If you start with this, it makes any conversions easy. In this case, we are wanting to convert degrees into radians. So let's use the unitary method, and we'll divide both sides by 180. See, why do we do that? Well, that gives us 1 degree. And the value of 1 degree is pi over 180 radians. Now that we know the value of 1 degree, we can easily find the value of x degrees by multiplying both sides by x. And so x degrees is equivalent to pi on 180 times x in radians. So that's the conversion that we want to use. We want to substitute x degrees for pi on 180 times x. And so when we make that swap, our integral now looks like this, where we are in radians. Now we can apply the chain rule. So we have the derivative of, the integral of cos is sine. So we have sine of pi on 180x. We have our constant of integration at the end, but remember we have to take care of the derivative of what's inside the brackets. We need to compensate for that. So we need 1 over this pi on 180. But fractions within fractions is never very nice. So when we have 1 over a fraction, that means we can just flip the fraction that we see. So 180 over pi is a nicer way to put it. And then here we could keep it in radians if we wanted, but the original question was given to us in degrees. So since pi on 180 times x is just x degrees, let's turn it back to x degrees now. And there is our final answer for example 3. And that finishes off our video. Great work.